I told you I was going to do an integral for you today, but then it occurred to me I've already done the integral for you and it took all lecture. So let me remind you which integral I said I was going to work through, and let me remind you where in lecture we actually did the whole thing. And then we can just kind of replace what we already know. So from last time, we are working out this Bayes factor corresponding to the Sharp test. So we're going to say we have some data coming from some normal distribution. I'll call this normal theta variance sigma squared. And we want to test something like this. Theta is equal to theta naught versus theta is something different. And so we're working through this Bayesian incarnation of everything. So I can set the problem up like this. And I can work out everything under this specification. But as you already know at this point, I can also do this. Say this is x bar. And this is coming from this distribution. And this problem has exactly the same properties. And because I've squared out the sigma squared. So this is the same problem. So what do we use to infer theta in this problem? We use x bar. It's sufficient for it. And we know the sampling distribution of this thing. If you take the joint distribution and you work through it with a product, that will work as well as doing this. It'll be exactly the same. Nothing actually changes. So this distribution right here for x bar is the same as the joint is proportional to the joint distribution of x1 through xn. And the data only comes through the form of x bar. So it gets reduced to that. So we were working through this Bayes factor. We wanted to work through this thing, square root 2 pi, sigma over root n, e to the minus 1/2 x bar minus theta squared over sigma squared over n, and then I'm going to have this delta function. This was our null prior that we're playing around with. We're going to integrate this, and it doesn't really matter if you like to think about this as integrating between negative infinity or infinity. You can think about it that way because this only takes on positive mass at a point. So there's only positive mass at one point, everywhere else it's 0. I haven't written down the denominator yet. Just if you're thinking about this right here, if you did the Riemann's sum argument for working through this integral, everywhere is 0 in the integrand except for this one point. Usually that one point is negligible compared to everything else and we can just throw it away. But since this is the only positive point in the whole integrand, that's the only thing that evaluates to something other than 0. And so if theta is in the null space, or if I integrate between negative infinity and infinity, we'd get the same answer. And this part of the integral, right here, it's easy to solve, and we just evaluate that at theta naught. So that's what we worked through last time. And then we have this other integral down here, where we were going to, same sampling function, or if you like to think of it as a likelihood, e to the minus 1/2 x bar minus theta squared over sigma squared over n. And then I'm going to integrate with respect to the alternative prior. And the alternative prior was a normal that we specified with some variance psi squared. E to the minus 1/2 is the distribution on theta. It's our prior. It's going to be centered at theta naught, our null hypothesis. I've got a psi squared down there. So I told you last time we were going to work through this integral, but then it occurred to me this morning as I started doing the steps, we've already done this. I was like, this seems eerily familiar. I've done this within the last couple months. We did this once upon a time with a predictive distribution. So as you might recall, we went through the excruciating details of solving this integral, fx tilde given mu. And there was a sigma squared in here. I'll write it in there. Sigma squared was known in this example. And then I have my posterior distribution on mu, given all of my data in sigma squared. So we did this back in the day of predictive distributions. So this was the predictive distribution, pi x tilde given x. And we went through all these steps. This thing right here was a normal centered at mu with variance sigma squared. And this right here was a normal centered at x bar with variance sigma squared over n. So we used the flat prior when we came up with that posterior. If you use the full-blown conjugate version, you'd come up with something that limits to this as well. So we did that a long time ago. Somebody help me out. What was the answer right here? I'll do the easy part. It was a normal. Centered at x bar. And what was the variance? Yeah, sigma squared plus sigma squared over n. And so we can apply all of that math to doing this integral. This is the same thing. This is a normal that we're integrating. It's centered at theta naught with this variance. This is the variance here, right here. So if I changed all of this, so if I changed this, if I just changed the context of all of this and just forgot about what the meaning of all these pieces were in here, and I wasn't thinking of it as the posterior predictive distribution, but instead I wrote x bar right there, I would have this divide by n over here. So that's the distribution for x bar. In this variance right here, this thing I would just center it, if you'd like, I'll say this was centered at x bar right here. We're going to change that to a theta naught. That's that theta naught right there. It's not centered at x bar anymore. And this variance was psi squared right here. So what would change in all of this? That's no longer x bar. That's the theta naught. That's where that one came from. And this one right here would be that one, psi squared. Now that might seem a little bit fast to you, but if it does seem fast and you don't remember the details, let me offer you a gift. If you work through this thing and show me all of the steps, I'll give you 5% midterm credit. So 5% midterm credit. If you don't do it, it won't be used against you in your total. So it's possible to get 105% in this class now. To show that this is a normal centered at theta naught with variance sigma squared over n plus psi squared. So show this. You can go back to my video where we work through all the details pertaining to the posterior predictive distribution and just copy those results, or work through it by hand. So I'd like you to show everything in excruciating detail if you'd like these 5% midterm credit. This would be due on Friday. I've given you a little bit of time to turn in the next homework, so hopefully that relieves you of some pressure. I don't imagine if you try to do this by scratch, from hand, it shouldn't take you more than a half hour, something like that. And if you watch my video and replace everything, it'll take you about exactly the same amount of time, because I went through it pretty slowly. So you can just turn that in on a piece of paper. You can handwrite it and just turn it in on Friday. I'll put it in my stack of extra credit. And so as I'm going through your grade, I'm going to calculate your grade, and then I'm going to go to my stack of extra credit and start adding in things for you. So write it up neatly, and just let me know that you know this. We'll go through this integral one more time in multivariate form. So when we're doing regression problems, we'll have a matrix analog of all of this. And I'll go through some of those details with you. Any questions about that? So we've done the integral already. So if you don't remember, this is an opportunity for you to do a little bit of practice and get some credit. Okay. So we're just going to use that result. So I can take this base factor, and I can write down what it is using that integration. We wrote this down last time. So this is going to be 1 over square root of 2 pi, just writing down the numerator first, sigma over root n, e to the minus 1/2 x bar minus theta naught squared over sigma squared over n. And this is going to be divided by that marginal distribution. So down here, I usually call this thing something like f of x bar. So that's the margin of the data. And we know what it is. So this is going to be psi squared plus sigma squared over n, square root of all of that, e to the minus 1/2 x bar minus theta naught over sigma squared over n plus psi squared. And we can simplify that a little bit. Just remember, when you're working through this integral, right here you'll pull out all of your terms that don't involve theta. You'll recognize the quadratic term and the -2 linear term, so you know what would integrate to 1. You can complete the square. It's going to be that e to the plus 1/2 e squared divided by e. That same calculation. You'll factorize out this x bar squared without losing it. Out in front of here, you'll figure out what the integrand is. Then you'll combine everything and you'll do that same exact trick again, and you'll recognize the quadratic term. You'll recognize the -2 linear term. So you have to do that twice. So I wrote down a slightly cleaner form of this integral. So this is just algebra. Let's not go through it right now. If you want to double check everything, that's fine. But let's do it later. Psi squared n over sigma squared to the 1/2. Give myself just a little bit more room. 1 plus psi squared n over sigma squared. Inverse, oops, not inverse. 1/2 e to the minus 1/2 x bar minus theta naught squared over sigma squared over n. And then there's this other factor in here. This looks like 1 plus sigma squared over n psi squared, and that's inverted. This is all in the exponent. Might not look exactly the same at first glance. Do some algebra, you can work out that these are identical to each other. So the nice bit is that we recognize that thing right here. So all I've done is I've just rearranged everything so I can isolate that term. And that's what we've called before is Zn squared. So that's that z-score. And so when a Bayesian is playing around with this, they consider a little bit more than the z-score itself. They're considering other things in this analysis. Let's just think about this as a function of a couple different things. So let's imagine that this was fixed. So let's imagine this exact same analysis that we've done before where we've considered a fixed z-score. And if you'd like a value for that, let's say it's like 1.97 or 1.96 plus epsilon or something like that. Let's say it's right about 1.96. You know which p-value that's associated with for this problem. Now I would have a p-value of 0.05 regardless of what n was. So if we computed z, so this is squared right here. So the z-squared score itself is 1.96. So regardless of what n is, if we saw a z-score of that, if you were a non-Bayesian, you would say, oh, that's presumably strong evidence to reject. Maybe that's not strong evidence. Maybe that one is. 1.96 minus epsilon. That's strong evidence to reject, right? It's 0.04999999. So presumably that's the lucky number that you're looking for. And if you do practice statistics that way, you're not alone, but shame on you. Okay, so let's just think about what all this means. Get rid of that. This is our base factor. So as n goes to infinity, let's just think about what happens here. So as n goes to infinity, this part right here, and I'm going to do a little bit of grad school limits right here if you want to work through and do L'Hopital's and be a little bit more rigorous in your limits, that's fine. So I would probably do that myself. But this thing I already know what it goes to. As n goes to infinity, that thing goes to 0 right there. So this term right here converges to 1. So this whole term right here converges to e to the minus 1/2 c squared. What does this term go off to as n goes to infinity? What's that?
Really big.
Really big. Yeah, so big that we can't even describe the number anymore, so we give up and we call it infinity. So this goes to infinity, half power of that thing, it's still going to infinity. So this thing right here goes to infinity times e to the minus 1/2 zn squared, which is equal to infinity. My calculus teacher would be appalled. So you get the idea. Take the limits, and that's what it looks like. So converges to that, it converges to that. So it blows up to infinity. So let's think about what that means in terms of the posterior probability. So the posterior probability of null, given all of our data, I'll write it down like this. This is what a Bayesian is giving you. They're going to give you 1 plus 1 minus pi naught over pi naught, Bayes factor, inverse, invert all that. So that's the posterior probability. This is really just Bayes' theorem in disguise. We can transform our Bayes factors to posterior probabilities. I always do this. So there's all these rules on, like, if a Bayes factor is between these ranges, it's moderate evidence. If it's, you know, bigger, it's strong evidence, something like that. I always just map it back to the probability so that we can have a coherent conversation about it. So maybe some people like 0.9s. Maybe some people like 0.95s. So there's nothing special about 0.95 in this example. The breakpoint is 0.5. So is what you might be thinking over here. So 0.95 would be extreme evidence towards the null hypothesis. So if this thing is going to infinity, the Bayes factor, then the Bayes factor inverse is going to 0 in all of this. And so that's going to 0, just as long as I have sensible priors right here that are not 0 or 1 on pi naught. This whole term will go to 0. And then I'll just have 1 inverse, which is just 1. So what that says is for fixed Zn squared, if it were 1.96 and n was really large, then you're thinking that the posterior probability is true. And that's the null hypothesis is true. And that's the argument I made last time. a couple times ago when we looked at just the z-score, and we thought about that numerator and the denominator, that if n were excruciatingly big, then I would think that the null hypothesis was correct if you gave me a z-score of 1.96. So it kind of depends on n. That's what the Bayesian is telling you. So the Bayesian has this gross disagreement with the non-Bayesian in this problem. Let me show you a few more numbers. So I wrote down some of these. Let's actually compute some sensible numbers here. So let's let pi naught be a half. Let's let psi squared be sigma squared. So I need to pick something so that I can compute all this stuff. What does that mean? If we ended up picking that, we know what that means. That means that I'm going to put half probability on each hypothesis. And I would think that if you're trying to be objective in some sense, that's reasonable. What does this mean to you? What it means is that your prior is worth one data point of evidence. So wherever you centered it, your prior weight has one data point worth of weight. And so this is a little bit questionable to do this, but I could probably defend it. I've seen people do this before. But let's just stick with that and see what we get. And I'm going to pick Zn is going to be 1.96 so that we understand what the p-value is that we're looking at. So let's just write down some values. So is n is equal to a range of different values. So let's write down 5, 10, 15, 50, 100, 1,000. And let's compute with our formula what the posterior probability of the null is, given x bar. So I wrote down these numbers. This is 0.331. For n is equal to 10, this is 0.367. For n is equal to 15, it's 0.4. So just if you want to know for this one, n is equal to 15, the base factor itself, I computed that as well. The base factor is equal to 0.66. If you wanted to look at that. So again, just plugging into this calculation, filling in all the placeholders, that base factor is 0.66, and that corresponds to a posterior probability of 0.4. So if n were 50, this is 0.521, so that would be our breakpoint right there. So depending on n, I would really change the way I thought about this level of evidence. 0.521. This is 0.6. This is 0.83. And we know what this one is. This one's 1. So again, the z-score was fixed at 1.96 for this. So that kind of goes back to our conversation that we were having last night about z is information in this problem. But depending on what n is, it changes my opinion about how strong that evidence is and in which direction it's leaning. And so I think it means different things depending on what n actually was. Now you could question all of these choices right here, but as long as you didn't pick something like 0 or 1 there, and you pick something reasonable over here, this trend would be the same. It'd be increasing. So for a fixed z-score. So when I see people work with p-values of 0.05 or alpha levels of 0.05 and they're looking to deduct it, and they think that this is strong evidence, I think there's more to the question. So what was n? And of course, what is your effect size that you're even looking for in the first place? And why did you even come up with that n in the first place? So if you did something sensible where you did a power calculation from the onset and you calibrated your effect size, figured out what n you would need to have a certain power to minimize, to bring down your type 2 error rate, then I might think you did something sensible. But if you just computed p-value and it ducked alpha and you're doing this sharp test, I don't think it means anything. And that's probably why BASP is taking such a strong stance. So BASP was noticing people had very large numbers right here. And they're noticing that in their journal, their z-scores were always just right below or right above 1.96. It's kind of a marvelous phenomenon. And so if you end up looking at the number of p-values that get reported out there, a lot of them are just barely ducking 0.05. Eric told me an interesting story that he read a paper last week where somebody computed two different p-values and they turned out to be exactly 0.05.
He reported that it's 0.05.
It's hard to believe, isn't it? So I bet they did a lot of wiggling around before they got there. So I'm surprised they didn't get it to be 0.049999. So at least it could be strong evidence. Let's look at another scenario. So hopefully this is starting to compel you a little bit that if you do use p-values and you're looking at z-scores, you probably want to think about n as well. So here's another analysis. Let's just look at our marginal distribution. This is the denominator. So our denominator term was this thing. Computing this exactly is the thing that you're getting the 5% for if you so choose it. So what does this look like? This looks like 1 over square root 2 pi e to the sigma over root n e to the minus 1/2 x bar minus theta squared over sigma squared over n. And then I have some alternative prior. So I'm just going to write that down as p to the h1 on theta. This is the contentious thing right here. So the alternative prior and how we're comparing our null hypothesis to something, that's all calibrated in that part of the prior. So this is very important. This is the part that had psi squared in it. And we kind of did this analysis where we had to pick some things. We had to pick that, and you might think, oh, I hate thinking about that and how much control that has over this problem. So let's just do something where we're just going to say this is proper. It's some proper distribution. Has to be proper in this case. If you did something improper, you'd get something nonsensical. Let me just describe that real quickly. So if we were to pick the improper prior, that would be same as psi squared going off to infinity. Look at where psi squared shows up. Right next to the ends, every single time. And so if psi squared is infinity, the alternative prior, this base factor is also infinity. And the posterior probability of the null is 1. And so what that means is that psi squared itself is calibrating the distance you need to be away from the null hypothesis before you're willing to reject it. If you take psi squared, you blow it out to infinity, and you're thinking about the improper prior, you're essentially saying you need to be infinitely far away from theta naught before you're willing to reject theta naught as a choice. So that kind of goes back to your question, Sam. Like, why do we have to change the prior for the test? If we use the flat prior, you would get a posterior probability of 1 on the null hypothesis. So that's not a good idea. But if you were trying to get something that was, you wanted a posterior probability on your null to be really high and nobody knew what was going on, you would just take psi squared and make it really big. And if you wanted it to go the other way, you'd make psi squared go real small. And so that's not fair game. So you're really comparing what is theta naught to everything else in the alternative space. And it's all about how much weight you're putting on that alternative. So remember what happens to that alternative distribution. If psi squared blows out, that distribution is flattening out and getting tinier and tinier. And so you're putting less and less weight on things that are close to theta naught. You're putting vacuously small weight. But because of the point mass prior, you still have a substantial amount of weight on theta naught, and it looks better than everything else. And so what the Bayesian is really doing is setting up a comparison. So you have to be thoughtful about that comparison. So I thought about your question a lot, Sam, and I really think it just comes down to this hypothesis test is just so, it's a misphrased problem. And it's not quite clear what you mean when you want to test that. So I think that's where the paradox really comes in. There's a disagreement as to what it means. And the Bayesian is setting up this very relative comparison, and they're being very specific about it. But it requires you to pick values like psi squared that the analysis is really subject to. That's called the Lindley-Bartlett Paradox. So let me just write that down real quickly, and then I'll tell you a little bit more about this that might satisfy you just a touch more. So the Lindley-Bartlett Paradox says, and there's two papers. There's one attributed to Lindley and there's one attributed to Bartlett, and they say different things, but this is the way the Lindley-Bartlett Paradox is interpreted. So as psi squared goes to infinity, i.e. alternative prior is flat. It's that aka non-informative prior, but it's super informative about the null. It's placing infinite mass on it. So if psi squared goes to infinity, the posterior probability of the null, given x, goes to 1. And so people like to call this the Bartlett-Lindley paradox. There's no paradox here. This is really just speaking to Bayesians and Neyman-Pearsonians. Sonians and Fisherians. I know they're different, but ultimately whatever you do, if you took P to be 0.05 as strong evidence or something like 0.05, this totally disagrees with that. So this is a total disagreement. Some people will use they'll invoke the Lindley-Bartlett paradox to say the non-Bayesians and the Bayesians totally disagree with each other. Some people will use it to say you can't use a flat prior in this testing. And so Lindley says one thing, Bartlett said the other thing, but they both agree with each other. So this is just for your vocabulary. There again is no paradox. There's just a disagreement on what we mean is theta equal to theta naught. So the Bayesian's going to be real specific about what close means. They're going to calibrate that through their alternative. Okay. That's troubling. But we could do something. We know we have to use a proper prior here so that we don't fall into this trap, that we're just getting extraordinarily high posterior probabilities, and it's because of something we didn't even think about. So I could say this thing is going to be bounded by this. 1 over 2 pi sigma over root n e to the minus 1/2 x bar minus theta hat maximum likelihood value over sigma squared over n ph1 theta d theta. So what I'm doing is I'm taking this part of the function and I'm just maximizing it. So this has some maximum somewhere. I'm integrating over this thing, but I'm going to integrate over something that's guaranteed to be bigger than it. And so it's going to bound this integral. And so that's a true statement. And this MLE exists. So if you've ever worked through a normal distribution and worked through its MLE, you can always find it. So this thing can be factorized outside of there because this is going to be a constant. It's not going to be a function of theta. It's going to have some input value right here. And so this is going to be equal to 1 over root 2 pi sigma over root n e to the minus 1/2 x bar minus theta hat MLE squared over sigma squared over n times this integral over a proper prior. I can do that integral. So keep in mind, I'm integrating between negative infinity and infinity over the whole entire alternative space. What's the value of this integral? It's 1, because it's proper. So it's normalized correctly. I need all those normalizing constants specifically worked out. So I'm left with this thing right here. So we don't even need that. And we're just left with that. What's the MLE for a normal distribution? It's x bar. So this is x bar. So this is x bar minus x bar. So that's 0 right there. And all I'm left with is this. So this is also 1. So we can get rid of that term as well. So this is bounded by that in all cases, regardless of how I pick psi, just as long as I made it proper. So this is kind of a worst case situation that we're looking at. So with that, I can work out a bound on the Bayes factor. So our Bayes factor, wrote this down in some numbers. So our Bayes factor, if we ended up computing this, this is going to be greater or equal to, we're not going to change the numerator in all of this, sigma over root n e to the minus 1/2 x bar minus theta naught squared over sigma squared over n. And I'm going to divide by this thing that we just came up with. So before I would have replaced it with this whole quantity, but this thing is guaranteed to be less than this quantity. In all cases, just as long as I use a proper prior, so independent of what I chose for psi squared. Make it as big or small as you want, just as long as you don't pick infinity. You don't pick 0, things like that. So you pick things that are within the valid range. Then this thing is going to be bigger than that. So this is smaller than something, so I'm going to divide by it, and it's going to bound everything in that direction. So this is going to be 1 over root 2 pi sigma over root n. That's just this part right here. These things cancel each other. And I can work out some posterior probabilities with all of this. So our posterior probability, just to remind you, it's this thing. This is going to be greater or equal to 1 plus 1 minus pi naught over pi naught. And then I can plug in this Bayes factor bound. I'll call it this. Bayes factor bound. I'll let you convince yourself the bound goes that direction. So you can work with it. So this Bayes factor is bounded in that direction when I invert it. This posterior probability is bounded in that direction. You can spend the 3 minutes convincing yourself which direction the bound goes. So the posterior probability is guaranteed to be bigger than that thing, more compelling. So I've worked out some numbers that we can look at. So let me write those down. So we'll look at this a little bit differently. So I'm going to pick pi naught, again, to be 1/2 on all of this. And then I'm going to look at varying degrees of Zn. So we'll look at the p-value. We'll compare those to the Bayes factor bound. We'll compare those to the posterior probability. And I'll write bound on this. So this is going to be my bound on that posterior probability. We'll look at some different values for Z. So we might be acquainted with some of these: 1.645, 1.96, 2.576, and 3.291. So the p-value associated with that, if you don't remember, it's 0.1. The p-value associated with 1.96 is 0.05. We're pretty familiar with that one. This is the 0.01 threshold, 0.01. And this is the 0.001 threshold. So those are the corresponding p-values. So a lot of times people will take that as strong evidence against the null. Let's see what a Bayesian thinks in the bounding case. And again, the posterior probability is guaranteed to be bigger than this. So our Bayes factors are 1, 3.87. This is 1 and 6.83. This is 1 and 27.60. This is 1 in 224.83. This has an associated probability of 0.205. This has a probability of 0.128. This has a posterior probability of 0.035. And this one is 0.004. Let's just think about what this means in terms of this column right here. So a lot of people have been taking p is equal to 0.05 as something that's really meaningful. A Bayesian would think that the odds of that, if you consider the Bayes factor that way, to be about 1 in 7, which would correspond to a probability of about 13%. So say that's approximately 13%. So the question is that strong evidence against the null? Keep in mind the posterior probability is guaranteed to be bigger than 13%. And I've made fairly objective choices. Pi naught is 1/2 on all of this. And then we got rid of what we needed to think about for psi squared. So independent of psi squared, I think the posterior probability is at least 13%. Question is that strong evidence? 13% or bigger. So if somebody said, I want you to bet your house on something, and your odds are 13% of losing your house, would you do it? I would not. So personally, I mean, I get it. You guys probably don't have houses, but whatever has a lot of value to you. So your car or something like that, I wouldn't take that as a super compelling thing. And the number is at least bigger than this. So I think what my point is 0.05 is not strong evidence against the null hypothesis. It never was. Any questions about that? So think about this a little bit. So there is this huge disagreement. And I think we can start to understand where that disagreement is actually coming from. That we just disagree on what the question actually is. So, but in any case, I don't think p-values that are around 0.05 in these sharp testing scenarios is strong evidence. So this is where the ASA Commission, the Bayesians got together and said, well, maybe we could take that as strong evidence. And they just kind of marched down this table a little bit and said maybe the new threshold for everything should be that. It corresponds to that p-value. I didn't like that because I thought people are just going to do the exact same game that they were doing before, and that's probably not the best thing to advocate. But I think in any case, we can understand there's problems with this problem set. We probably need to see how this stuff works in practice. So what I want to do when we come back around to this problem is study it in model selection, and I'll let you guys do some comparison in the next homework. Let me just read you this comment that Jim Berger wrote. This kind of stood out at me. This is from his Statistical Decision Theory and Bayesian Analysis book. Jim Berger is since retired. He's an emeritus faculty at Duke. He spent a lot of his career at Purdue. And he was a frequentist. And he started looking at decision theoretic properties of Bayesian analyses. And that's what compelled him to be a Bayesian. It wasn't like, oh, the subjective nature of everything, I like that. You know, personal probabilities. That wasn't what was doing it for him. And Gibbs sampling wasn't even a big deal at that point. So it was all this decision theory and things like this that kind of changed his mind. But he wrote, the conflict in the above example, so the example is this one that we're studying, is of such interest that it deserves further investigation. A Bayesian analysis can of course be questioned because of the choice of prior. The assumption of the normal form for G can be shown to have no real bearing on the issue unless x bar minus theta naught is large. I think it matters. So, but Jim's allowed to disagree. He's earned that right. And the choices of setting the centering parameter to be theta naught and pi naught are equal to 1/2 are natural. Indeed, if one were trying to be objective, these choices for the centering parameter and pi naught would seem to be virtually mandatory. I think I agree with that. One could certainly question the choice of the alternative variance, psi. Jeffries in 1961 argues for such a choice in objective testing, but the answer definitely depends crucially on the choice of that alternative variance. Jeffries actually prefers a Cauchy form for the prior, but again, the form matters only in extreme cases. I like the Cauchy form too. We just can't do the math on the chalkboard. And then he says this, when answers heavily depend on features of the prior, such as the alternative variance, Bayesian has no recourse but to attempt subjective specification of it. And so it says at the end of the day, you have to think about what that means in the context of your problem. And again, it's calibrating how far from the null you would have to be before you're willing to reject it. And I think that means different things in different problems. What do I advocate? Try not to do this. Try to just do estimation. Saying that, we're going to come back to model selection. I think there is no real recourse. You have to do something. So I'm going to present you with several different model selection techniques. But on Friday, I want to give you a prelude to some extra credit. So if you're not inclined to do the extra credit, you can just wait for the video. But I'm going to introduce you to the Variance-Fisher problem, and I'm going to give you an extra credit homework assignment for it. And for that one, I'll give you 15% midterm credit. So you might be incentivized to come and check that out. I'll also provide you with a little bit of sample code that I'll post on the website. But let me explain that on Friday, and then we'll come back to this problem in a grander problem. Thanks, you guys.